During this module, we will conclude our basic manufacturing statistics study with a brief look at linear regression and modeling data. Anywhere there's data in manufacturing, there's an opportunity to model patterns evident in that data. Applications could include forecasting demand or backlog, understanding key drivers for yield, waste, or cycle time, predicting inventory shortages, or simply inferring relationships between physical variables like size and weight. The outcomes for this module include applying regression analysis to manufacturing data and measuring model performance and uncertainty. In our original case study of TV bracket manufacturing, we sampled brackets from the assembly line and measured length and weight for the purpose of making a shipping decision. We desired to use statistics to better understand our data, and in particular, we wanted to understand the relationship between bracket length and weight. We first started by looking at basic descriptive statistics of our data. For example, for the weight variable, we counted the number of samples, 11, computed the maximum, 10.84, the minimum, 4.26 pounds, the average of 7.5 pounds, the standard deviation of 2.03 pounds, and the variance of 4.13. This is useful information, but it doesn't exactly tell us about the relationship between length and weight. To better understand the relationship between length and weight of the brackets, we plotted the data and then we added a trend line. And with that trend line, we also fit the parameters of a linear regression model. This is an inferential statistical model that tries to figure out the best relationship between length, the input, and weight, the output. It uses a simple form y equals a1 times x plus a0, where x is the length and y is the weight. A1 and A0 are model parameters, effectively the slope and the intercept, respectively. When we fit this data, we computed the R-squared as a performance metric of 0.67, and the general visualization of this data shows a positive trend, a positive relationship that's not perfect. There's some noise evident in the data, but a linear enough relationship that we can establish that yes, there is a positive relationship between length, the longer the length, and weight, the more the bracket weighs. To improve our confidence in these results, we took some additional data. We had 3 more trials on top of our first trial for a total of 4 trials of length and weight samples. We wanted to understand this data and do similar types of analysis to what we did in the very first case. We used a spreadsheet to analyze the data and look at the same statistics, max, min, average, standard deviation, and variance, and also the linear regression values for the slope, intercept, and R-squared. Many of the values were the same in each of these trials, averages, standard deviations, variances, for example, and also the slope and intercept were the same along with the R-squared. The only thing that we saw different was the max and min. We again put all of our data into a single scatter plot of weight versus length, and we generally saw that there was a positive linear trend as we'd seen in the previous regression analysis. In fact, when we add the trend line to the data, we can see with the equation at the top the slope of 0.5 next to the variable x and the intercept of 3, also with an R-squared of 0.66 or 0.67. In the next step of our analysis, we computed a polynomial fit for our weight and length. We looked at a polynomial up to 6th order, meaning that the variable x we took to the power of x to the 6th, x to the 5th, 4th, 3rd, 2nd, and just length x. And we tried to find coefficients that fit the relationship between weight and length subject to this model. Now, the R-squared using the least squared process improved. It went up from 0.67 to 0.7 for this model. We might call this a nonlinear model in one sense because of these higher order polynomials. However, in another sense, it's really just also a version of a simple linear model. Now, the key thing here is that we see that the data has a little bit more squiggle in it, and as it goes through the bulk of our linear trend, we can see that there's some curves, but then also between 14 and 18, The nonlinear or the polynomial model predicts that our weight to length relationship starts to reverse, and that as length increases, weight starts to go down all the way back up to 18, where we see a positive higher weight for a higher length. Is this data correct? We're sort of inferring what's going on between 14 and 18 without much data. Our linear model predicted a straight line through that. So this is an interesting example of a comparison between two models. There might be something that indicates that we are overfitting our data with this more complex model. Now our analysis got a bit more interesting when we made that same scatter plot, but we colored each of the trials differently. We also used different marker shapes: squares, diamonds, circles, and triangles. Now, with this data, we still have a slope of 0.5 and an intercept of 3.0, and a nice trend line that looks positive going up with an R-squared of 0.67. But the additional layering of colors and shapes gives us some indication that there might not be a linear relationship in all of our trials. And when we made separate tiles or separate windows for each of our trials with the same scatter plots of length and weight, we began to see the pattern emerge. Of course, our first trial in the top left had our general linear trend with some noise around that linear trend line. But our second trial clearly indicates a different relationship, something that's more quadratic. And in the bottom left, our third trial indicates a perfectly straight line with the exception of one outlier. That one outlier is pulling that trend line to look identical to the other lines. And then in the bottom right corner, we have probably a test equipment issue where most of our data is just reading a constant length at 8 with a little bit of noise in the weight measurement, except for one top right triangle there that's reading about 19 inches and about 12 pounds. This tells us that maybe a linear model for all this data isn't quite right. And this example is called Anscombe's quartet, and it's a classic way of demonstrating how there can be some challenges when we simply model data with whatever model we think happens to fit our data, without having to look perhaps at the relationship here, where we can see the model could be improved by different types of relationship. Here we see what happens when we improve the modeling. In our top left linear model with our original trial, we still have 0.5 slope and an intercept of 3 with an R-squared of 0.67 or so. But then look what happens when on trial 2 we change the model to be a quadratic. In that case, the quadratic perfectly fits our data, and the R-squared is exactly 1, the best possible R-squared we can have for our model. We can see that there is a quadratic term, a linear term, and then also a constant as well. In the bottom left corner for trial 3, we see what happens when we take out that single outlier. Our slope goes from 0.5 down to 0.3454, and our intercept changes slightly also and goes up to 4. But what's really interesting is our R-squared now is perfect at 1.0. Now, sometimes when we see an R-squared of 1, we have to be very cautious about the results. That might indicate in natural data that there's something more likely to be wrong with our modeling process. And then on the bottom right model, when we have almost certainly some kind of mistake in our measurement, in our data, it's not even worth modeling. It's really just a constant relationship. There is no relationship. It's a constant model. That single point in the top right is most likely also just an outlier, and it's not worth actually modeling the data, even if a model would generate the same kind of results in that corner as the top left. A variable, or in particular a measured variable, is often a function of one or more variables, often one or more independent variables. Regression establishes the functional relationship between dependent and independent variables. The classic simple linear regression model is noted y equals a0 plus a1x, where x is the independent variable, d is the dependent variable, and the parameters are a0 and a1 for this model. A0 typically considered the intercept, and a1 called the slope. Often this is put in the form of y equals mx plus b. A similar model, technically also a linear model, but with higher order terms, is called polynomial regression. In this case, we still just have x and y, but x is taken to the higher power, in this case up to the nth order power. In either case, we're using least squares to attempt to find the model parameters by minimizing the sum of squared errors between the actual data and the model fit. So our objective function is to minimize the sum of the difference between each data point and the curve fit, y sub c. We square that up, we sum that, and we try to minimize that with some type of regression process. One of the key things in finding the best fit is establishing some measure of performance. And one of the simplest measures of performance is called the standard error of the fit. In this case, we square all of the deviations from between the model and the real data, sum them up, divide by the degrees of freedom, and take the square root. We call that the standard error of the fit, S sub yx. As shown here, we can use the standard error of the fit to understand uncertainty and error of our regression model. The confidence interval can be approximated by student's t times the standard error of the fit, syx, divided by square root of n. We see that visualized as constant dashed lines around our linear curve fit y sub c and the plot on the right. We can be more accurate in our confidence interval by including the x variable as well, and the difference between the x and the x mean squared is in this equation called the Sheff equation, can be used to show how the band of our confidence interval for our uncertainty and error analysis actually expands out at the tails for variables closer to the ends of our x range. The coefficient of determination, R squared, is the most common performance metric used in regression analysis. It represents the proportion of the variation in the dependent variable, y, that's predicted from the independent variables, x. This is usually used in the context of statistical models whose main purpose is either prediction of future outcomes or the testing of hypotheses. The most general definition of R squared is 1 minus the ratio of the residual sum of squares to the total sum of squares. SS sub res is the cumulative sum of squared errors depicted in blue, while SS sub tot accounts for the average value of the dependent variable, and it's depicted in red, with SS sub tot equal to the difference between each value and the mean squared and summed up. In the best case, the model values exactly match the observed values, and there's no error, and that results in SS sub res equal to 0 and an R squared of 1. A baseline model based on this measurement always predicts y, the average value, and will have an R squared of 0. Different fields often have differing standards for what constitutes a good model and a good value of R squared. But R squared generally ranges between 0 and 1, and higher values indicate better fitting models. There are certain cases where R squared can yield negative values, and that arises typically when the data used for the analysis wasn't accounted for in the modeling process. For example, when we're analyzing out-of-sample test data. So in summary, R squared provides a measure of how well observed outcomes are replicated by the model based on the proportion of total variation of outcomes explained by the model. It's not the only measure of regression performance. Other goodness of fit measures include MSE, mean squared error, RMSE, root mean squared error, MAE, mean absolute error, AIC, a K-key information criterion, and BIC, Bayesian information criterion. The correlation coefficient, lowercase r, measures linear correlation between two sets of data, sometimes called the Pearson correlation coefficient. It's the ratio between what's called the covariance of the two variables and the product of their standard deviations. It's essentially a normalized measurement of covariance so that the results always have a value between -1 and 1. This measure can only reflect a linear correlation of variables and ignores other types of relationships or correlations. As a simple example, one would expect the age and height of a sample of children from a primary school to have a correlation coefficient that's significantly greater than 0, but less than 1, as 1 would represent an unrealistic or perfect correlation. Also from our case study, the length and weight of our TV brackets would also have a positive correlation. When only the intercept is included in a linear regression model, the R-squared value is simply the square of the correlation coefficient. Some example scatter plots with different correlation coefficients are shown in the image on the right. When we modeled the 4 trials before, a 6th-order polynomial model appeared to improve regression performance, at least as measured by R-squared. But the resulting model yielded suspicious results that do not likely reflect underlying behavior, especially in the area between 14 and 18 inches where we had little data. This 6th-order polynomial is likely too complex. The model will likely not generalize well, meaning that we suspect it will perform poorly on unseen data. One way to improve model validation is to fit or train our model only on a portion of our data and evaluate performance on an out-of-sample test subset. Here we look only at trial 1 data, and we use a random variable to split our data roughly into half for training and testing partitions. Our previous model without partitions yielded the relationship y equals 3 plus 0.5x with an R-squared of 0.67. With labels for each case either as training or testing, we can model the data where we only use the training data shaded in blue for modeling with linear regression. Here we actually see the training performance drops to 0.397 for an R-squared, and the slope and intercept parameters change. We see a shallower trend line going through the blue training data on the plot. And the plot also shows our out-of-sample test data in red. The linear regression modeling process has not seen the test data, so it more fairly evaluates our model. We compute R-squared on the test data with the columns on the right, and the R-squared is of course 1 minus the ratio of sum of squared residuals to total sum of squares, referencing the average weight. The test R-squared in this case is 0.485, a little better than training, but worse than our original performance. While this training and testing partition method may appear to hurt model performance, the validation discipline of holding out test data should give us a more realistic view of how the model will perform on new data. We previously looked at the least squares methodology as minimizing the sum of squared errors of the actual data in the model fit. The standard error of the fit, S sub yx, is used as a basic measure of performance and particularly used for confidence intervals for the fit, where we use students t, and we can also use Sheff bands to establish a confidence interval. We can develop similar standard errors for the slope and offset parameters, and these help us develop what are called precision estimates of the uncertainty of those parameters. So A1, the slope, is plus or minus students t times S sub A1, where S sub A1 is the standard error of the slope, defined as the standard error of the fit SYX times the square root of 1 over xi minus x bar squared. Similarly, the standard error for the intercept, S sub A naught, can be used to establish a precision interval for the intercept parameter as well, A naught plus or minus students t times SA0. These standard errors are most often seen and used in measurement applications. We'll finish our regression and modeling section with an example problem. Here we have experimental measurements that are taken from a physical system, and they can be modeled by the relationship y equals b times x to the nth power. There's some experimental data provided. Our job is to find the coefficients to fit the model using the method of least squares and calculate the standard errors for the fit. We'll use a spreadsheet, and data is provided in the course page as well. We'll convert the nonlinear logarithmic model into a linear least squares regression problem, and we'll use the linest functions to get our model parameters and our standard errors. We could also use the slope and intercept and trends functions in Excel as well. Here we see a copy of our spreadsheet data for the logarithmic regression problem. Our problem presented us with 5 different data samples, x and y, and we're fitting the relationship y equals b times x to the m. So to get that into a linear form, we have to take the log of both sides, compute log of x, log of y, and then we can use the slope and intercept functions to find m and b. We can get from capital B, we can get our lowercase b back by just using b equals 10 to the capital B power. So the linest function is also a capability in Excel or Google Sheets that not only gives us the slope and intercept, but it gives us our standard errors, our R-squared, our F statistic, and a couple other measures as well. There's a corresponding spreadsheet that follows this that's available on the course page. Here we see a plot of our data for the raw data in X and Y form on the left, which shows our power relationship, our logarithmic relationship. On the right, we've taken the log of y and the log of x, and so it looks like a straight line. Hence, our linear regression model is going to do a great job of fitting this data. For our final regression example, we'll take a look at fitting linear relationships for the 4 pairs of data provided here. We'll also estimate the standard error of the fit, look at the degrees of freedom, and then show uncertainty bands on a plot. X and Y data are shown on the top left, and then various calculations along the way are shown to build up our confidence intervals with Sheff bands. The slope is 2.6 and the intercept is 9. We're using the linest function to compute that, and R-squared is 0.91. We also get an F statistic and a degree of freedom calculated, which happens to be the number of samples 4 minus the number of parameters 2, so the degrees of freedom is 2. We need the student's t, and so we can look that up from a student's t table. We choose 95% because we don't have any other indication of what confidence we should use. We look up the student's t value, and then we use that as a multiplier times our standard error of the fit, along with our values based on the average x and the average residual between each x and the mean squared. So the plot on the right shows how our confidence bands, our Sheff confidence bands for our X and Y data generally shows a linear relationship. This is the kind of analysis that we do for any type of measurement application. So this concludes our module on regression and modeling data. In summary, we've applied regression analysis to several data examples, and we've measured model performance and uncertainty.